Hello, my name is Rana Kolta, and it's an honor to be able to present my work at the JP University in India. My presentation for today is about a hybrid demosaicing algorithm using frequency domain and wavelet methods. The outline of my presentation is as follows. First of all, a brief introduction on how digital cameras work is necessary for us to understand where demosaicing came from and what is its purpose. And then I'll start talking about two demosaicing algorithms, the first being color plane interpolation using alternating projections and frequency domain demosaicing. Finally, I'll present my proposed demosaicing method, which combines these two algorithms to further enhance results. Introduction. As most of us know, a digital camera is composed of a series of lenses that focuses light onto a semiconductor device that records light electronically. The image sensor employed by most digital cameras is a charge-coupled device that transports the charge through the chip, and an analog-to-digital converter measures the amount of charge and transforms it to binary form. A charge-coupled device is a grid of photosites. Each photosite represents a pixel in a digital image. However, each photosite is colorblind, meaning it only captures the light intensity. For it to capture color, it must be overlaid with a color filter. Highest quality cameras use 3 separate sensors. The first technique of capturing color is by using a beam splitter. The beam splitter splits the light into 3 beams, each directed onto a different sensor, and each sensor is overlaid with a color filter, one red, one green, and one blue. However, cameras that use this technique tend to be bulky and expensive. The most popular way of capturing color is by permanently overlaying the image sensor with a color filter array. A color filter array is a color filter composed of red, green, and blue samples arranged in a certain pattern. In this diagram, it shows us an example of an image sensor overlaid with a color filter array. Now each photosite will represent only one color, either red, green, or blue. The most common color filter array is the Bayer pattern, and here's an example of it. And as we can observe, the green samples are twice as much as the red and blue samples. And that's because the green samples represent the luminance component, and the human eye is more sensitive to the luminance component than the chrominance components. The advantage of using a color filter array is that now only one color filter array is required, not 3. Only one charge-coupled device sensor is needed, no beam splitter is necessary, and all color information is recorded at the same moment. Cameras that use this technique are smaller and more economic. However, the trade-off of using a color filter array is that the output of the sensor is not a full color image. However, it's a mosaic of red, green, and blue samples. Therefore, a process is required to reconstruct this mosaic back to its full color image. This process is known as demosaicing, which comes from the word mosaic. Demosaicing algorithms could be embedded in a camera's microprocessor or could be implemented as a separate computer software. Here is an example of an image before being demosaiced. As we can see, it is composed of red, green, and blue samples. And what we're trying to reach after demosaicing is a full color image. The goal of demosaicing is to estimate the 2 missing color values at each pixel location in a color filter array. However, demosaicing can cause erroneous estimates that may lead to a phenomenon known as color artifacts. Erroneous estimates are inaccurate estimates of the missing pixel values. Good demosaicing algorithms always try to find ways to reduce these color artifacts. I'll now start talking about the first demosaicing algorithm, which is color plane interpolation using alternating projections. It was proposed by Gunturk in 2002. Gunturk had 2 observations made. The first one was that false colors or color artifacts are primarily the cause of high-frequency region crosstalk, such as in edges. The second observation is that the green samples on a color filter array are twice as much as either the blue and red, which naturally means it preserves more details. As an overview of his algorithm, an initially demosaiced color filter array using any simple demosaicing algorithm, say by linear interpolation, is decomposed into its 4 wavelet subbands, and the high frequency component of the red and blue channel are replaced by the high frequency component of the green channel. And that's because green preserves more details. This algorithm is iterative. This is a block diagram to further clarify Gunturk's algorithm. Step 1 is to initialize the algorithm using any simple demosaicking algorithm, such as bilinear interpolation. Step 2 is to decompose the green channel into its 4 wavelet subbands and update it. This is a visual aid to help me explain the updating of the green channel of the initially demosaicked image, of course. Consider that this is a fully demosaicked image, and the colors represent the observed data of the color filter array. I'll then extract the estimated green pixels at original red and blue pixel location to create 2 subsample images. I'll then decompose the green subsample image at an original red to its 4 wavelet subbands. I'll do the same for the green at original blue. I will replace the high frequency component of the green subsample at original red with the high frequency component of the red observed data. I'll do the same for a green at original blue. I replace its high frequency component with the blues. I'll then reconstruct the 2 subsample images and return their updated pixel values to their original locations in the large image. Step 3 is to decompose the demosaicked image once more time into its 4 wavelet subbands, of course after updating its green channel. Step 4 is to replace the high frequency component of the red and blue channels with the high frequency component of the green channel. Step 5 is to reconstruct the image back and replace pixel values at color filter array locations with observed data. This is because the observed data at these locations can be altered due to the replacement of the high frequency component of the red and blue channel with the green. And it is important to preserve these data because they are more fidel and accurate. Step 6 is to repeat step 3 to 5 until 5 iterations or until we can reach a stopping criterion. However, 5 iterations were used in Gunturk's algorithm and it provided good results. The second type of demosaicking algorithm I'll be talking about is frequency domain demosaicking. This method was proposed by Dubois in 2005. It is a very special algorithm because of the way it perceives the color filter array. It perceives the color filter array in its frequency domain representation. And in this diagram is an example of a frequency domain representation of a certain color filter array. It is composed of a luma component at the center and 2 chrominance components C1 and C2. C1 is located at the edges, while there are 2 copies of C2, one horizontal and one vertical. And we can observe that there is a crosstalk between the luma component and the chrominance component C2. This crosstalk causes color artifacts at the demosaicked image, or at the final demosaicked image. Dubois was able to find a relationship between the luma component and chrominance component C1 and C2 with the red, blue, and green channel of the reconstructed image. Through mathematical derivation, he was able to express this relationship through matrix notation as follows. So, if we were able to extract the luma component and the chrominance component C1 and C2 successfully, we will be able to restore the full color image. We can extract the luma component from the color filter array using a low-pass filter, and the 2 chrominance components C1 and C2 using appropriate bandpass filters. In the first diagram, it shows us the filter used to extract the chrominance component C1. The second diagram shows us a filter that was used to extract the horizontal chrominance component C2. The third diagram shows us the filter that was used to extract the chrominance component C2 at its vertical location. There are 2 copies of chrominance component C2. However, we only require one chrominance component C2 to be able to reconstruct the full color image. So the question is, which one should we choose? Should we choose the horizontal chrominance component C2 or the vertical? As we recall, there was evident crosstalk between the luma component and the chrominance component C2. So it's important to choose the chrominance component C2 that suffers least crosstalk. Dubois was able to solve this problem by estimating local energies as C2 locations. using Gaussian filters. And a weighted decision was made using the following equation. C2 is equal to W times C2 horizontal plus 1 minus W times C2 vertical. And W is a weight, which is EY over EX plus EY. And EX and EY are local energies estimated by filtering the color filter array using a Gaussian filter. This Gaussian filter, as we can see, was used to estimate the local energy at a horizontal C2 location. And this Gaussian filter was used to estimate the local energy at a vertical C2 location. By measuring the local energies, this decision or this equation will let the C2 copy that suffers least crosstalk to be more dominant. And by this, we will be able to reduce color artifacts introduced by the demosaicing algorithm. The luma component will be the color filter array minus the chrominance component C1 minus chrominance component C2. Now that we have successfully extracted the luma component and the chrominance component C1 and chrominance component C2 that suffers least crosstalk, the red, green, and blue channels of the reconstructed image can be estimated using the matrix notation as follows. And by this, we will have reconstructed the full color image. I just wanted to end this section by showing you a visual comparison between Gunturk's method and Dubois' method. And here's an example of what I'm just trying to say, color artifacts. Shades of red, yellow, and blue hues that are undesired, erroneous, or incorrect estimation of the missing pixels. In Dubois' algorithm, the same artifacts are still there but are less visible. I will now present my proposed demosaicing algorithm, which is the hybrid use of Gunturk's and Dubois' algorithm. Frequency domain and Gunturk's demosaicing algorithm do provide excellent results. However, as we've just seen in the previous slide, color artifacts still prevail in high frequency regions such as edges. Therefore, the proposed hybrid use of both algorithms showed a noticeable decrease in these artifacts. As we can remember, Gunturk's algorithm had to be initialized by a simple demosaicing algorithm. So instead of introducing Gunturk's algorithm with a coarse demosaicing algorithm that produces coarse estimates of the missing pixel values, I thought of introducing it with good estimates of the missing pixel values using the frequency domain demosaicing. And now Gunturk's algorithm could not be perceived as a demosaicing algorithm anymore, but as a post-processing method to Eric Dubois' algorithm. This experiment showed an increase in the cumulative peak signal-to-noise ratio and a decrease in the color artifacts. Here's a block diagram that shows my proposed demosaicing algorithm. The color filter array is demosaiced first of all using frequency domain demosaicing, which was proposed by Eric Dubois. And then it will be post-processed by Gunturk's method, which is to decompose the demosaiced image into its 4 wavelet subbands, replace the high frequency component of the red and blue channel with the green, reconstruct the image, replace pixel values at color filter array locations with observed data, and I will iterate this post-processing method for 5 times until termination. Here is a visual comparison to compare between demosaicing a color filter array using frequency domain alone and after using the hybrid proposed method. As we can see in the first image, color artifacts are available or can be seen around the edges of the window, and after post-processing it with Gunturk's method, these artifacts are not visible anymore. In the second image, there's a yellowish tint to the fence of the house, and after post-processing it with Gunturk's method, this artifact is no more available. The fence is back to its white color. As well, there's some artifacts around the fence, the picket fence over here, and after post-processing it, it's no more visible. And in the second image, there are some artifacts around the edges of the windows of the house, and after post-processing it, these false colors or color artifacts are no more visible. For numerical comparison, the cumulative peak signal-to-noise ratio was tested for the 24 codec images. set before and after post-processing, and there was an increase of about 0.6 decibel achieved. The codec images are found online, and I will reference it at the end of my presentation. However, not all images require post-processing. Images that don't contain a high content of edges should not be post-processed, since post-processing does consume time. Frequency domain demosaicing produces good demosaiced images. It only introduces artifacts near the edges. Therefore, the edges of the demosaiced images is extracted using the canny edge detection. And if the mean value of the edge map is higher than a certain threshold, then I post-process the image. Otherwise, it was left alone. And the threshold chosen for my paper was 0.019. Here is an example of an image after extracting its edges, and as we can see, it contains a high content of edges, which leads to a high mean value. This image will require post-processing. By this, I'll have reached the end of my proposed method, and as a conclusion, the hybrid use of frequency domain demosaicing and Gunturk's demosaicing algorithm reduced visible color artifacts around the edges of the reconstructed image, and the cumulative peak signal of noise ratio has increased as well. By this, I'll have reached the end of my presentation. For any questions, please feel free to